I'm going to give you 8 quant questions. They start easy, but question 6 breaks almost everyone. Keep track of your score and don't cheat. Alright, question 1. This one looks easy, but don't rush it. A stock drops by 10% on Monday, then rises by 10% on Tuesday. Is the price now higher, lower, or the same as it was originally? Most people say, the same. That's wrong. Let's break it down. Imagine the stock starts at $100. A 10% drop takes it to $90, but 10% of 90 is only $9. So the new price is $99, not $100. You lost money, even though it went down and back up. If that surprised you, question 3 is going to mess with your brain. Alright, question 2. This one's a free point if you stay calm. What's the expected value of rolling a fair 6-sided die? Don't overthink it, you just average all the outcomes. So the answer is 3.5. Even though you can't actually roll a 3.5, on average, that's what you get over time. Alright, feeling confident? Good, because now it starts getting weird. Alright, question 3. This is where people start getting it wrong. A family has 2 children. You're told that at least one of them is a boy. What's the probability that both children are boys? Most people say 50%. That's wrong. Let's list the possibilities, but we already know there's at least one boy, so we eliminate girl and girl. Only one of those is 2 boys. So the answer is 1 out of 3, not 1 out of 2. If that confused you, good. That means you're actually thinking. Drop your answer for the next one in the comments, and let's keep going. Alright, question 4. Now we're stepping it up. On average, how many coin flips does it take to get 2 heads in a row? This one's not obvious. The answer is 6 flips. Yeah, more than most people expect. Here's the intuition. Every time you flip a head, you're close. But if you get tails, you reset. So you keep losing progress, and that pushes the average up. But here's where it gets interesting. If instead you're trying to get head and tail, it only takes 4 flips on average. Same coin, same probabilities, completely different results. If that doesn't feel right, good. Question 6 gets even worse. Alright, question 5. This one feels impossible at first. 100 people are boarding a plane. Everyone has an assigned seat, but the first passenger lost their ticket. So they sit in a completely random seat. Now every person after that, they sit in their own seat if it's free. Otherwise, they pick a random open seat. What's the probability that the last passenger sits in their correct seat? This looks like a nightmare, but the answer is 50%. Here's the key idea. As people sit down, the situation keeps passing the problem forward. Every time someone finds their seat taken, they basically become the new random chooser. So what actually matters is the final moment. When the last passenger is about to sit, there are only 2 seats left, the first passenger's seat and the last passenger's seat. If the first seat is taken, the last person gets theirs. If the last seat is taken, they don't. There's no bias. It's completely random between those 2. So the probability is 50%. If you didn't see that coming, you're starting to understand how deceptive probability is. And now, it gets even worse. Alright, question 6. This one sounds impossible. An ant starts at one end of a 1-kilometer rubber band. It walks forward at 1 centimeter per second. But here's the catch. Every second, the rubber band stretches by another 1 kilometer. So the band is growing way faster than the ant is walking. Question is, does the ant ever reach the end? It feels like the answer should be no, but it's actually yes. Here's the key idea. The ant isn't just making absolute progress, it's making percentage progress. In the first second, it walks 1 centimeter out of 1 kilometer. That's a tiny fraction. Then the band stretches, but that tiny fraction gets stretched too. Next second, it adds another tiny fraction, and that gets stretched again. Then another, and another. So its progress looks like this. These tiny pieces keep adding up. And here's the crazy part. This sum doesn't stop. It slowly, but surely, grows without limit. So eventually, after a very long time, the ant reaches the end. If that just broke your brain, subscribe. The last 2 questions only get worse. Alright, question 7. This one's brutal. You take a stick of length 1 and break it at 2 random points. Now you have 3 pieces. What's the probability that those 3 pieces can form a triangle? This is not obvious at all, or 3 lengths to form a triangle. No single piece can be longer than the other 2 combined. In this case, that simplifies to none of the pieces can be longer than half the stick. because if one piece is longer than 0.5, the other two together are less than 0.5. So now the question becomes, what's the probability that all three pieces are less than 0.5? It turns out, if you map all possible breakpoints, only a small region works, and that region is exactly a quarter of the total. The answer is, if you got that one, you're seriously good. But the last question? This one's the final boss. All right, final question. This one sounds completely impossible. There are 100 prisoners. Each one has a number from 1 to 100. In another room, there are 100 boxes. Each box contains one of those numbers, randomly placed. One by one, each prisoner walks in and can open 50 boxes. If they find their own number, they survive. If even one person fails, everyone is executed. No communication, no hints. So the question is there a strategy that gives them more than a 30% chance to survive? It feels impossible. Random guessing gives you basically zero chance. If you just pick 50 random boxes, your chance is 50%. Sounds decent, right? But all 100 prisoners need to succeed, so that's 0.5 times 0.5 times 0.5, 100 times. That's basically zero. But here's the trick. Each prisoner starts by opening the box with their own number on it. Inside, they find another number. Then they go to the box with that number. Then repeat. They're not guessing anymore. They're following a chain. These chains form loops, called cycles. For example, box 1 says 42. Box 42 says 7. Box 7 says 1. That's a loop. Now here's the key. As long as every loop is 50 boxes or shorter, every prisoner will find their number within 50 steps. And the crazy part, this strategy works about 31% of the time. But why? Remember, everything depends on those cycles. If even one cycle is longer than 50, the prisoner in that cycle won't find their number in time. So the whole problem becomes, what's the probability that a random shuffle has no cycle longer than 50? Now here's the key insight. In a completely random arrangement, long cycles are actually rare. There's a small chance of getting a really long loop, like 60, 70, even 100. But most of the time, the cycles are shorter. When you add up all the cases where every cycle is 50 or less, it comes out to about 31%. So it's not luck. The strategy works because it turns randomness into structure. Instead of guessing, you're systematically exploring a loop. If you made it this far, you're thinking differently already. Comment how many you got right, and subscribe if you want more problems like this.